Hello, today we'll be talking about the Kullback-Leibler divergence, which is a distance measure between two probability distribution. So, divergence is also known as KL. So typically in reinforcement learning, we don't want the new policy to deviate too much from the reference policy, so we add the KL divergence loss to constrain the model updates. So let's take a look at what it is. So suppose we have two probability distributions P and Q, then the KL between P and Q would be the log would be the expectation of the log of px over qx. And in a discrete setting, so this would just be some x px times the log of px over qx. So now let's take a look in the LLM case. In the LLM case, we have, so assume that now we have some input x, which is the prompt, and then we have some output, which is the generated sequence. So let's call this y, which is a sequence of all the tokens. And now when we're training, we have the new policy, which we call pi theta. So y x, and the O policy, which is, call this the reference, and we want to measure how much the new policy has deviated from the old policy. And so we can use the KL divergence between two of them. So KL of the pi reference of y given x, and this will just be the expectation of the log x over pi theta reference of the output sequence given the input prompt. So now what does this mean? So in the RL setting, computing the full KL might be too expensive because we have to get over all the different sequences. So the way that we can do this to estimate this is to use a single sample estimate. So here we'll define the single sample estimate of that particular sequence. So this would be the single sample estimate, and the single sample estimate would just be the log of this. And based on the log identity, we can actually split this up to be minus and what is actually the probability of the sequence given x? This would effectively be, so the probability of the output given the input x would just be the product of generating every token. So what this means is that this quantity, so if I write it here, minus log is equal to the log of the product of the probability of every token under the new policy minus the log under the old policy. Which is the reference. So the product and again we can use the log product identity, so this becomes sum over every token log and we can group them, so both becomes a sum, so minus log pi data reference of new token. So what this actually is so again we have the identity, so we can divide it. So it will be the sum over every token of the log the over the pi theta reference of each token given the input and the previous tokens. And what this quantity is, so what this quantity is exactly the sample estimate of the KL of that of generating that particular token. So this will be sum of the KL of every single token. So you can see that the KL for the individual tokens would be the KL for the over across the whole sequence would be the same as the sum of the KL of the individual tokens. Yeah, and this is how the so this term is the loss that you usually see in LLM KL. Yeah, that's all. Hope you enjoyed it and look forward to the next one.